Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is the second part of a lecture on solving small linear systems. We're using some algebraic methods here, specifically substitution and elimination, or elimination, I suppose. We just finished a lecture on substitution method, and I just wanted to let you know that the applications, there are quite a few applications that you're going to go through in your course in intermediate algebra concerning or involving systems of equations. However, I'm not really focusing on those right now. I will do a lecture in a little bit on applications, and I'll focus specifically on just doing non-stop applications with systems of linear equations. But in this video, we can go ahead and concentrate on the elimination method. That's the common name for it. A lot of people know it by that. Some people know it by Gaussian elimination, and others might know it as linear combinations. What I'm going to do is start by just justifying the elimination method. Now, you may already know the elimination method, but you might not know why things work the way they do with the elimination method. So I think that it's a good idea to justify the elimination method. So let me write down a few equations here, like 2x equals 12, and maybe 5x equals 30, and 3x minus 1 is equal to 17, and x equals 6. We'll look at all four of those equations just to talk about what they have in common. And maybe I'll even write down that question. And if you look at each of these equations, numerically it doesn't look like they have anything in common until you start solving each of them. The first equation, the solution to it is x equals 6. The second equation, the solution to that second equation is x equals 6. The third equation, actually, if you let x equal 6, that also solves that equation. And finally, the last equation, if you let x equal 6, that's a solution to that equation. So they all have the same solution. Now, one thing I want to convince you of, it's very easy to convince you of this, would the solutions to any of these change if I were to write them in a different order? In other words, if I were to write it instead as 2x equals 12, x equals 6, 5x equals 30, and 3x minus 1 is equal to 17. Would the solutions still be the same, or would they change? And the answer is that they would stay the same. So I want to write that down. Even though it's a very trivial statement, it needs to be written down. And it's extremely obvious to see. But this next one might not be. So what would happen if I were to, let's say, take one of these equations? It doesn't really matter to me. Let's go ahead and take this one. I'll call this row 3. Okay. Let's take row 3 and multiply it by a number. Let's say, I don't know, let's do like 10 times row 3. I'm going to take 10 and multiply it by that third equation right there. And what I'm going to do notationally is just say that that becomes my new row 3. Now, for right now, I just need you to kind of absorb what I'm telling you, and then we'll discuss why I'm using this notation. It's a little bit easier to use this notation. So I'm taking row 3 and I'm going to multiply it by 10, and I'll replace that and make that my new row 3. If I do that, well, then my first two rows are the same. 2x is equal to 12, x is equal to 6, but my third row I've multiplied by 10, so now I have 50x. And when you multiply a row, you multiply both sides. It's an equation, right? You can't just multiply one side of an equation by a number. You have to multiply both sides of an equation by a number. Now let me ask you, has any of the solutions changed here? Well, if you look through, x equals 6 is still a solution to the first, the second, and the fourth equation. And if you look at the third equation, if you plug in 6 for x, it's still a solution. So this is kind of an important note. So let me write this down. I was pretty technical with how I wrote this down. If we multiply an equation by a non-zero constant, in other words, if we just multiply both sides of the equation by a number, as long as that number is not 0, then the solution remains the same. If I had multiplied that row 3 by 0, I would have had 0 equals 0. There's no way to determine what x could have been then. So you have to make sure you multiply by something non-zero. Okay, I kind of believe that. The last one is actually the trickiest. And then we'll go into what the elimination method's all about. But up to this point, you might be just asking yourself, what's the point of all of this? And I can understand that. So the last little one I'm going to do here, maybe I will go ahead and erase this stuff up top so that I can use some extra space here. And I'm going to ask you, what happens when I take this multiple? Let's just say we take this multiple right here, the one we just created, and, oh, I don't know, let's go ahead and subtract off this row right here. Okay, so let's take 50x equals 300, and let's subtract off that top row, which is 2x equals 12. Now, using a better notation, I would have said, let's take row 3 and subtract off row 1. Because I am taking row 3 and subtracting row 1. But there's something interesting that happens here. So 50x minus 2x is 48x. And 300 minus 12 will give me, what is that, 288? And it turns out that if you were to, let me just double check my math, 290, 288, yes. When you divide both sides by 48 to solve for this, it turns out that x is still 6. It turns out that the solution hasn't changed. So let me write this down as a final note here. And notice on my note, I call this the kill step, because this is probably the most important step in the elimination method process. So let me just read this out loud. If we add or possibly subtract a multiple of one equation from another or to another, the solution remains the same. And we saw it right here. We took an equation and we subtracted an equation from that. Both these equations have the same solution, and I took one of them and subtracted it from the other, and we get a resulting equation here. 48x is equal to 288. When you solve that, it turns out it still has the same solution. In other words, a solution never goes away. It doesn't go away if you swap the orders of the equations. It doesn't go away if you multiply an equation by a non-zero number. And it doesn't go away if you take a multiple of one of these groups of equations here, this group right here. If you take a multiple of that group and add or subtract it from another one in that group, still the solution doesn't go away. Turns out that this is the crux of the elimination method. It's better if I just show you an example to begin with, and then I'll actually write down the steps to the method itself. So here we go. I'm asking you to solve this system by elimination. And of course, we haven't really written down the steps to elimination, but the idea is still the same. That you can rewrite these in any order you want. I'll call this row 1 and this row 2. So I could swap the rows if I wanted to. But that's kind of a useless thing. And in fact, that idea of swapping rows is only powerful if you're going to learn matrix theory. And that's not what I'm going to discuss in this topic or this lecture at all. Although it's a wonderful way to solve large systems, it's kind of useless for us right now. So swapping the row idea is not that big of a deal. However, we have two other things we can do that I know that if both these equations have the same solution, which I want them to, I want to know when are their solutions exactly the same, then by that previous example I just did, and let me just show you, by this example right here, I know that I can multiply one of the equations by any number I want, or I can even add the equations or multiples of the equations to each other, and it will not change the solution. So let's pick a variable, and let me write that down actually properly. And I write it as pick a variable to kill off. I basically want to make a variable disappear. And what I'm going to do is I'm going to kill off y here. I'm going to choose to kill off y. And I'm going to do this by taking row 1 and adding it to row 2. By the way, you'll never see me subtract, except for that very first example I did a few moments ago, you'll never see me subtract equations. I always find a way to add them up. It leaves any error with subtraction out of it. Subtraction's not my strongest suit. I know I'm a mathematician and I should be able to subtract all day long, but the fact is, for some reason my brain has always had a hard time with certain subtractions. So, let's go ahead and add row 1 to row 2. If I do that, well, let's see. I'm going to write it out in slow form here. I have row 1. I'm going to add it to row 2. So you start asking yourself, what's x plus another 2 of them? Well, it's 3 of them. What's y plus a negative y? Well, that's why I chose to add these up, because y plus a negative y is 0y. This is the only time I'm going to write 0 in a variable. I'm just doing that to show you that that's what it is. 18 plus 12 is 30. So you get this, 3x is equal to 30. Or in other words, x is equal to 10. It happens so quickly that sometimes people think, wait, I must have done something wrong. But in reality, it can happen very quickly that you get to a solution. Of course, this is only half our solution, right? We need to find out what y is. And at this point, to find y, you're going to have to substitute this x equals 10 back into one of these equations up here. Well, it doesn't really matter to me. I think I'll substitute it into the first equation here. So row 1, I'll let x equal 10 and subtract 10 from both sides. We'll find out that y is equal to 8. So my solution is x equals 10, y equals 8. If you have an instructor that wants this in point format, that's 10, 8, right? X and y. Now before I walk away from this example, I just want to let you know that I didn't have to kill off y. I could have killed off x here. But it seemed to me, since these y's were already opposite each other, that it was, at least their coefficients, it was much easier to kill off that y variable. Had you chosen to kill off x, you could have. And let's go ahead and show how that's done. So let's pretend that we're going to kill off the x here instead. So if I'm going to do this, I have to it's my plan to make the coefficient of that x, this little number right here, I want it to be the opposite of this number 2, so that when I add up the x's, they disappear. And the only way I'm going to do that, let me label these rows, row 1, row 2. The only way I'm going to do that is to take negative 2 times row 1 and make that become the new row 1. If I do that, let me rewrite. So I take negative 2 and I'm going to multiply it by everything in this first row. So in other words, I have a negative 2x, I have a negative 2 times that y equals, and I also have, and this is a very, very important thing to mention here, a negative 2 times that 18, which is a negative 36. Most students I know end up forgetting that to multiply the right-hand side. I'm just letting you know, be very aware you're going to get a wrong answer if you forget to multiply the right-hand side. Since I didn't bother touching row 2 here, I'll just rewrite row 2 as 2x minus y is equal to 12. Now what I'm going to do, I see that the coefficient of the x's are opposites, so I'll go ahead and kill off x by taking row 1 and adding it to row 2. Here's row 1, and I'm going to add this to row 2. Write a little plus sign there. Negative 2x plus 2x, that disappears by design. And so we have a negative 3y is equal to negative 36 plus 12 is a negative 24. And when you divide both sides by a negative 3, you get y is equal to 8. Well, if y is equal to 8, go ahead and box that up, I could plug that value of y into any of my equations. This one, even these two over here, but I probably wouldn't because they just look worse. So I'll probably plug it in this top one, the very first equation here. So I have x plus my value of y is equal to 18. Subtract 8 from both sides to get x is equal to 10, which is exactly what we got a moment ago. So I could have solved for x, or killed off the x variable. So now that you've seen this in action, let's go ahead and write down the steps for the elimination method. So here it is in all its glory, the elimination method. The first step here is actually the same. I should have written it down in the very first lecture on this in this topic, but it applies to the substitution method as well. First true step to solving a system is really to get rid of fractions if we can. So clear any fractions or decimals. We'll do an example where I show you how to do that. Pick a variable to kill off. Usually you try to, always, you try to pick a variable that's quick, that's already opposite. It's the same variable in the other equation or whatever. But if it's not, if there's just no variable, if both x and y in both equations don't have opposites in the other equation, then you're going to have to do some multiplications. So step 3 is to multiply one or both equations by a non-zero constant so that the variable you want to kill off has opposite coefficients. Once you do have those opposite coefficients, you add the equations, that variable disappears, you only have an equation with one variable at that point, and you go ahead and solve. So let's put this to use. You probably should write that down, pause this or whatever, and then write that down. And then once you're ready and you have it written down, go ahead and press play, and you can follow along on these examples I'm about to do. I always recommend as well to pause. Once you see my example, pause it, see if you can figure it out. If you can't, then you can press play and see what I do. And if you can fast forward. So here's a system of equations. Solve this system where you have m over 4 is equal to n over 3 minus 5 over 12. Second equation is n over 5 equals 1/2 minus m over 10. I'll go ahead and label these as row 1, row 2. That way you could see kind of my operations as I go through. First step is always, if I have an equation, to always clear fractions. So the LCD for that top equation, I'll just write it above it, the LCD, is 12. That's what all the denominators in that top equation divide nicely into. So I'm going to multiply the top equation by 12. So in other words, 12 times row 1 will become the new row 1. That's a great way to write it down because then you don't have a mess all over the paper or anything like that. Also, remember, when I first introduced this section, I showed you that multiplying an equation by a non-zero number doesn't change the solution. So this is not going to change the set of solutions at all. Here I go. If I multiply the left-hand side by 12, I'll get 3m. The right-hand side by 12, I'll get 4n minus 5. Now let's go ahead and do the LCD for the row 2, the bottom equation. That LCD is 10. All those denominators in the bottom equation go nicely into 10. So I'll take 10 and multiply it by row 2. That'll become my new row 2. Let's see what happens. If I multiply row 2 of the left-hand side by 10, I'll get 2n. Multiply the 1/2 by 10, I'll get 5 minus, and then m. This is my row 1, this is my row 2. So it was very nice that it ended up like this. We get these nice whole number coefficient or integer coefficients. That's the point of using multiplication by the LCD so that we don't have to deal with fractions. Now, something that I didn't really mention, it's kind of an important step here, I should have mentioned it maybe in that list, is to rewrite your equations so that all the variable terms are on one side. In other words, in this first row, I'm just going to subtract 4n from both sides, so I get 3m minus 4n is equal to a negative 5. In my second row, I'll go ahead and add m to both sides, so I have m plus 2n is equal to positive 5. That's very important because if you don't do that, you can't really stack the equations nicely. You have to stack them to where you have the like variables above one another to be able to do the elimination method. Now we're going to go ahead and pick a variable to kill off. It doesn't really matter to me. M looks like a great candidate, but I'm actually going to kill off the n's. The reason why is because they're already opposite in sign, so I only need to multiply that first or that second equation by the number 2. So if I multiply row 2 by the number 2 and make that my new row 2, I'll get to where the coefficients of n are opposites. So let's go ahead and do that. So row 1 didn't change, so that's just 3m minus 4n is equal to a negative 5. Row 2 is just twice. Everything's twice what it was before. So I have 2 of those m's, positive 4 of those n's equals, and remember the right hand side you also multiply by 2, so that's 10. And at this point I see since the coefficients of the n's are opposite, I'm just going to go ahead and add row 1 to row 2. When I do that, you know that these n's will cancel out nicely. So let's go ahead and write the addition. It's pointless for me to actually have rewritten this. After a while, you kind of do this stuff in your head, but I still wanted to kind of take my time with this so you could see the steps here. 3m plus 2m is 5 of those m's. The n's disappear, and negative 5 plus 10 is a positive 5. So in other words, m is equal to 5. Now that I know what m is, I can go back and resubstitute it into any of my previous equations. Now let's take a look at all of our previous equations we have here. We have a lot of them, right? We have 1, 2, 3, 4, 5, 6, 7, 8 of these equations. And it doesn't really matter which one you plug it into, but I highly recommend that you don't plug it into the one with the fractions just because it's a mess. It's really just not any fun. I will probably just plug it into, it looks to me like this one right here is a good one to plug m equals 5 into. So I'm going to go ahead and do that. I'll just write 2n is equal to 5 minus the value of m, which is 5. So I get that 2n is equal to 0, or in other words, n is equal to 0. And there we have it, our solution. This is the point where these two equations meet. At m equals 5, n equals 0. 5 comma 0 if you're graphing it out. And that's also the values of m and n where both these equations have the same solution simultaneously. So let's do another example. So this will be a very brief example just to kind of show you how to do this stuff. In this case, yes, it would be very easy to kill off the x variables here. I would just multiply row 2 by 2. In fact, let me label these row 1, row 2. But I want to give you an example. Well, maybe I have another example coming up where I can make one up where we have to multiply both equations. Just in case we don't, though, let's just pretend you wanted to kill off the y's. Okay. So if you want to kill off the y's, you don't have to. Like I said, you do the x's. But if you want to kill off the y's, you would have to make the coefficients on the y's opposites. And to do that, I would probably multiply row 1 by this number right here, by 2. So 2 times row 1 will become the new row 1. And then I would multiply row 2 by a negative 3. So essentially what you're doing is if you want these two to be opposite, well, I'm going to multiply this by 2 and this by negative 3. So this becomes a 6 and a negative 6, and then they're opposites. So essentially what you do is you multiply by the other coefficient and make sure that one gets an opposite sign on it. If you do that, then you get something of the form, let's see, so we get the following. 2 times row 1 is going to be 4x plus 6y is equal to a negative 32. And then negative 3 times row 2 is going to be a positive 3x minus 6y equals a negative 3. And now when you add these up, you'll get that 7x. So now we can do the addition step. And I told you normally I don't rewrite it. Well, this is what I usually do. I just go ahead and add from here. I get 7x is equal to a negative 35. Or in other words, that x is equal to a negative 5. Some people think, well, it's going to take forever if you go about it the way that, if you choose to kill off the y's. It's not true. It's just an extra little headache, but not much of one. And then, of course, to find the value of y, you could plug this negative 5 for x into any of the previous equations. I will choose this one right here. So I have a negative 5 plus 2y is equal to 1. That's positive 5. I'll subtract from both sides. And then divide by 2. Y is equal to a negative 2. But again, you could have done this very easily just by multiplying the second row by 2 and adding up the equations. But I'm just showing you what happens if you have coefficients that aren't easily made opposite. You can still do it. Now, I don't want you to stop this video and think you're done, because there's some big concepts coming up here, and I disguise them with easy examples. In fact, a lot of my examples tend to be easier. But let's go ahead and solve this one really quickly. Pick a variable you want to kill off. Here, let's just kill off the p's. So to make the p's opposite, I'll multiply row 1 by a negative 2. So negative 2 times row 1 will become the new row 1. And remember, my goal here is to kill off the values of, or the coefficients of p. So row 1 becomes a negative 12p minus, again, multiply each object in row 1 by a negative 2. So minus of 4q is equal to negative 2. And again, the second row I didn't do anything with, so it's 12p plus 4q is equal to positive 2. Once you do this, you're going to add rows 1 and 2, right? Because row 1 plus row 2 will kill off the p variable. Negative 12p plus 12p, that's gone. Negative 4q plus 4q, strangely enough, that's gone as well. Negative 2 plus 2, that's also gone. So what happened? Well, if you get to where no variables are left, but you have something that's true, that's actually true. This is called an identity. Whenever I see something like 0 equals 0 or 1 equals 1, in other words, if you don't have any more variables and it gives you like a number is equal to itself, then you know that's always true. It's always true. So what that's essentially saying is that there's these two equations are always the same. There's always a solution. There's an infinite number of solutions. And what does that mean? Let's see. Let's recall some stuff that we talked about in a previous lecture. If you have an infinite number of solutions, in other words, that any value for p and q will make this system true, that means that the two lines that you were to graph here are the same exact lines. So that must mean that this is a dependent system. Dependent. Some people call it dependent equations. I usually call it dependent system, but it is technically, I think, dependent equations. It's consistent because there is a solution, and it's dependent because there are an infinite number of them. So if you get down to the format where number equals itself, it is a consistent and dependent system. It does happen every once in a while, especially in advanced mathematics. You often get equations that, or systems of equations that have infinite solutions. Here we go again. Just another example here. Solve this. I will probably still use elimination to solve this, although substitution can be used as well. What I'm going to do is rewrite it to where I get all the variable terms on one side. And now once I've done this, I'm going to go ahead and let's kill off the m variables. So I'll multiply row 1 by a negative 4. That'll become my new row 1. Let's see what this turns into. We get a negative 8m minus, plus, because we're multiplying by negative, so negative times negative becomes plus. It's plus 4n is equal to a negative 4. And in the second equation, 8m minus 4n is equal to 3. Looks somewhat similar to the last example, but it's not. There's something significantly different about it. So I'm going to add these two equations. I have no values of m left over. I have no values of n left over. However, negative 4 plus 3 is a negative 1, and now you ask yourself, when is this true? It's not. It's called a contradiction in mathematics, but whenever I teach it in a classroom, I just basically say it can never happen. So it's never true, which essentially means there's no solution. There's no way that the system has a solution. Well, if I have a system of equations, remember these graph is lines, if there's no solution, it means they don't cross. They don't touch or anything. They must be parallel but not touching. Well, if that's the case, these are called inconsistent. So this is an inconsistent, I think I just spelled that wrong. Inconsistent. There. Well, there's an S in there. Inconsistent system. So this happens when algebraically, when you solve it, you get something like 7 equals 5 or something that's not true. Once you know that's not true, then you know there is no solution, which means it's an inconsistent system. So just to recap really quickly, all we talked about, which is quite a bit in this lectures, the last two lectures, we introduced an algebraic method for solving a system of equations. The algebraic methods are substitution and elimination. And both of them are fair game, and you should be able to use both. Although the one that gets used more often than not, actually, well, it depends. I think they both have their uses, but elimination gets used quite a bit in the real world. And then you just got to know that algebraically, if you try to solve a system and you get down and all your variables disappear, and you end up with something like 5 is equal to 5, or in this case 0 is equal to 0, or 10 is equal to 10, something that's always true, then you know that those actually represent the same graph. They're parallel and on top of each other. So they're consistent and they're dependent. However, if you go to solve it and all variables drop out, and you end up with something that's weird, like 3/5 is equal to 27 or something like that, you know that's not true. Never true. And in fact, there's no solution. That implies there's no solution to that system, which means that when you graph it, they're just parallel and never touching. Inconsistent system.